Oh, and there's a recording in progress. I'm real big on having my participants develop an intuitive understanding of regression. I mean, you know, we will do some math and all that stuff, but lots of times for the math, I'll say, hey, the next few pages are math. So if you want to see the math proof or see the math derivations, actually, they're not really proofs, there they are. If you want to see them, away we go. If you don't want to see them, yeah, me either. So let's turn about 4 or 5 pages in and we'll keep going. But the math is there if you want it. But oh my gosh, it's not a math course. You know what? It's not a software course either. So, you know, at the level of regression 2, whatever software package you want to use, that works. Between myself and my 2 awesome TAs, we can help you with SAS, SPSS, Stata, R, Python. Yeah, I said SAS. One of my TAs actually knows SAS. So yep, no problem. If I left anything out, sorry, I left it out. So software is not an issue. We can help you with whatever software package you choose. Now, for my in-class examples, I do use SPSS because it's just so super easy to pick up and learn. So you do have that going for you, but don't take the course because I use SPSS for the in-class examples, and don't avoid the course for that reason either. I'm telling you, we've got you covered. You will be okay, I promise, when it comes to software. Don't forget, the goal is to develop an intuitive understanding of this material so that you can do your own work better and evaluate the work of others better. That's the deal. There'll be plenty of applications, but what I said about the intuitive approach. You'll be challenged in this course. Guarantee you'll be given sufficient support to meet that challenge. It's not easy work, but I think it's fulfilling work. I try to present the material in 3 different languages. Words, whole bunch of words. Math, I've already told you, not as much math as you might be expecting, and a whole bunch of pictures, a whole bunch of visualization stuff. That's the deal. Lots of topics covered. I start off with, this is a mean. I mean, we start at that level. And the first day is pretty much a review of basic stats, and we build from there. Then we get into bivariate regression, multiple regression, lots of diagnostic residual plots, transformations, curvilinear regression. I don't like that word though. Multicollinearity, lots of F-tests, tons of F-tests, some of them old school, some of them pretty, relatively new over lots of material. Logistic regression, heteroscedasticity, weighted least squares, generalized least squares, autocorrelation. I know I'm leaving some stuff out, but the point here is we go from the very, very basics all the way up to some pretty advanced regression stuff. So that's what you have to look forward to. Here's my style of teaching. You'll have access via daily modules on Canvas. At the end of a class day, I'll publish the module for the next day. So about 20 some odd hours before the next class starts, boom, that module will be published on Canvas. There'll be several documents in there. There'll be some maybe data files and data examples in there. And there'll be a total of 7 optional learning exercises in the course where here's a bunch of questions and here's a tutorial and answer key, not just the answers, but also a tutorial. And I've prepared about 900 pages of lecture notes. This greatly reduces the number of notes you have to take during class. Not to 0, but it reduces the notes you take during class so you can actually spend class time paying attention. You'll have access to those documents as well. And that's how I'll run the class. I'll build it around those lecture transcripts. Don't worry. I will not read the notes. Oh my God, the exact opposite. That's how the class works. Plenty of times for discussion. I run a laid back class. If you want to ask questions, ask questions. If you're online, you can ask questions via chat and the TAs will be there. A couple of questions. Will the class review the assumptions of regression? Oh, we're going to spend a lot of time on assumptions of regression. You bet we will. And what's the other question? How much review will be done in the beginning of the course? Again, we'll review statistics in the course, but for sure, and we'll build up. But let me emphasize, this is not a course on software. So we will not review how to use specific software packages in the course, but you'll see that as we go along and you'll have the opportunities to develop that, especially in meetings with me and with the TAs. Let's go. Any other questions? Oh, one more. Let's see it. What are the requirements for assessment grades? That was next. Thanks for asking. The way I assess is at the end of the course, I will give an exam. You'll have between 24 and 48 hours to take the exam. The questions will be intuitively based. No hardcore math, nothing like that. But you'll have probably about 15 questions and you'll answer about 10 of the 15. You get to choose which 10, but even more important, you get to choose which 5 you don't answer. And that's how the assessment will work, the grades. For those of you interested in grades in graduate school, that's how that will work. That's pretty much the course. Any other questions? Any questions? Now I'm going to go back and get something to eat. Thanks very much.
And you all are doing a really great job with the polite, gently, not everybody at once, back to getting sweets. Nicely done. Something I forgot to mention regarding grades that I could have mentioned earlier in the form of a reminder. So ICPSR summer program is neither a credit nor a grade granting institution. You will all get participation, a certificate of participation that lists the courses for which and the lectures for which you have registered. And then if you would like, you may, for these methods courses here in the last 3 weeks of the program, if you like, it's entirely your option, you may request a grade letter memorandum, which is not a grade. It's a letter from the instructor that says, if I were teaching this course at my institution, student would have earned an A or whatever, you know, an A or whatever, right? And that's it. And your home institutions use these certificates. Lots of home institutions, I understand, use these certificates and these grade letter memorandum. Some employers use them to see whether they reimburse you, for example, things like that. So you may use these however you want to use them. Grades, entirely your option. If you do choose a grade letter memorandum, you must let the instructor know, and then you must do the work in the scheduled time in order for them to grade them, because they're not working anymore after the session is over. So that's the only stricture on that one. Okay, great. So then next up is rational choice theories of politics and society, Jim Johnson. And Jim is here indeed. And Jim, you do have slides, right? I do have slides. All right, I will. I'm having difficulty. This mouse is too sensitive. From beginning, go.
All right.
And you can use that if you want.
And how does this work? All right. So this morning in the staff meeting, we were talking about championships, Manchester City, and my wife is from Stockport, and told me that when we got together that I could root for any Premier League team that I wanted, as long as it was City, and surely not the tourist team from across town. So having irritated many people in the room already, we'll start. I've been doing this workshop for, I don't know, a long time. And mostly what it's meant to do is be a sort of lead up to proving theorems. And John and Maggie are coming back, right? Rob?
John and Maggie are not. Paul Smaldino is coming, and he's going to teach a course in modeling social behavior.
Okay, so in the second session, there's a really high-tech class. This class, like the first two, is decidedly low-tech. It's meant to really give you some idea of why you would want to put yourself through the pain of doing all the math to learn how to do game theory and social choice theory. That's not a costless enterprise. And I don't care whether you do that or not. It's sort of your choice, but this will give you reasons for or against that. And it starts with this, this paper by Ariel Rubinstein. Ariel Rubinstein invented non-cooperative bargaining models, and those are theoretically essential given what we know about the indeterminacy of strategic interactions. And I wanted to put this up there because he makes some really strong claims. Without a proper interpretation of the enterprise, game theory is useless, utterly useless. And then he says such an interpretation is the essence of the theory. If you took a game theory class, mostly that kind of question is not even on the agenda. You start in, you do utility theory, you start proving theorems and doing homeworks and pretending that the math is the most important part of the enterprise, when I think that that's just a mistake. And it's nice to know that people other than I think that too. So Ariel is a good friend in that regard. When we talk about an interpretation, we're going to talk about the interpretation of particular components of models. Why do we assume completeness in a utility function? What does that do for us? What theoretical leverage does that give us? We're going to talk about canonical models like Rubinstein's bargaining model, the Nash bargaining model, and so on. And we're going to ask questions about the entire point of making formal models in the first place. And I think that the standard reason that social scientists think that they make formal models is just wrong. And so that's where we're going to go. Here's Rubinstein. Game theory concerns the real world. That's right. It's not just pure mathematics, but it also does not concern the real world the way most of you think by pointing and making predictions. I have an equilibrium. Here's a hypothesis. It must be there in the world someplace. Let's go look for it. That takes out about 99% of the rationale most social scientists would give you for engaging in this enterprise. Instead, he says it's an analysis of concepts, and I think he's just right. It allows us to say, what do we mean by some abstract concept like institution or deterrence or rationality in some specific context? And then we can take that understanding and plug it into our hypotheses and empirical studies, but the models themselves are not empirical. And that's usually people are running for the door at that point, but you shouldn't. What we're interested in is how do we get an interpretation like this that gets us from math to ordinary language and back again, right? And that's, I think, a crucially important undertaking in social science that's mostly ignored. Intellectual battle lines. Oh, that's not it. Oh, so we have a standard interpretation, and I use John and Maggie, John Patty and Maggie Penn, because they've taught here in the second session before, and that gives you the sort of standard rationale, right? Solve for an equilibrium, treat it as a hypothesis, and look for evidence for or against that hypothesis. They like this idea so much that they say the exact same thing 3 times in the same book. So it's got to be really important, but they're not alone. Becky Morton and Keith Dowding define formal models in terms of making empirical predictions. So it's definitional. That's what a formal model does. My former student, all of these people, by the way, are friends and colleagues and former students, so I pick on them in person as well as in settings like this. Josh Clinton tries to give us a story about ideal point estimation in terms of testing formal models. That's what we use that technology for. Jonathan Woon says the same thing about experimental methods. We justify doing experiments because, among other things, they allow us to test formal models. And my colleague Kurt Signorino, in a really influential paper, gets us down to the nitty-gritty of what would it mean to test a strategic model where everything's interdependent with a set of causal models, logits and probits, that assume that our observations are independent. Guess what? They don't talk to one another. So there's a whole set of people out there who think that what we do with models is point and test, predict and test. And I think that that's mistaken. You can think of this as fantasy football. You probably don't want to do that, but you could. There's the correct view, and then there's the right view. And the right view is the people defending the notion that we predict and test with our model, with our formal models. And the correct view is my side. And so being correct and not being conservative are both, they map onto one another nicely there. And these are all people, right? Nobel-winning economists and philosophers of science. My advisor, Elster, is on the right side or the correct side here, and so on. It's not that we don't have people that give us portions of this alternative story about conceptual analysis. It's that we don't have people who have put it together, who have taken the small bits and pieces and given us an alternative story. This one, we're done. And so, just so you know, I don't care whether you come out of the class thinking what I think. What I care is that you come out of the class knowing that you have to think something about these interpretive issues. If you disagree with me, I'll be happy. If you sit there and think, just let me solve the theorems, I'll be unhappy. And to give you some idea that I can persuade other thinking adults of this, there's some shameless self-promotion, a couple of papers out there in the world. This may make me look smart, or it may raise questions for you about those outlets and whether you ever want to submit papers to them again, but that's neither here nor there. I'm happy to answer a question. We're going to look at lots of models. There will be only words and pictures with a few equations thrown in as a kind of garnish. And the whole point is meant to get you to think hard about how formal models fit into the enterprise of doing good social science. Nothing I say is meant to try and persuade you that this is not good social science or that you shouldn't do formal modeling. You should. But I teach at the University of Rochester. They would lock my door and not let me in the building if I said you can't do formal models. It's a bad idea. So
We got two chatted questions for you, Jim.
Oh.
One very practical one wants to know about assessments and how much stats background might be needed.
Zero stats background.
And assessments?
Assessments, if you're taking the course for a grade, I ask you to write a couple of little papers, 5 pages, on something that we negotiate, you and I. Mostly I push people to do something that's actually valuable to them back home, and fitting in, making a bridge between what they're doing at home and what we cover in the class.
Okay, another question is, would this be friendly to an interdisciplinary, cross-disciplinary approach?
Absolutely.
And what time is the course?
8:30 in the frickin' morning. That's a technical term.
Right, that's the technical term for it. Indeed. More questions from the
Any other
audience here?
questions?
Yes, sir.
Yeah, how does this kind of relate to the theoretical modeling and empirical modeling next course? Like, what's the overlap and what's
So repeat the question.
What's the relationship between this and the second session course, modeling of social behavior or something?
Oh, which did you mean?
the theoretical one and the one you teach?
The one I teach a course on empirical modeling for positive theorists.
Oh, you're doing it
Next session.
next session. So my course is going to get you to ask questions about why you would ever take Rob's course. And to have an answer to that question that satisfies you and satisfies Rob and satisfies me, even if we disagree about those things. So from my perspective, a lot of you are political scientists. There's this thing called the empirical
Implications of
theoretical models. That's an oxymoron. The theoretical models are conceptual. They're about concepts, not about empirical things in the world. And so I say that in public places and my friends get mad. What are friends for, right? But
I think Jim would be really surprised, actually, if any of you are still around for the second session. I teach a course in empirical modeling, so I don't say EITM. I say EMTI, empirical models of theoretical intuitions. You wrote the model to simplify how the world works. That's the same thing you want to do with your empirical model. You want a useful simplification that you can carry around about how the world works, and you want to try to estimate its empirical manifestation. We could talk more about that later if you want, but I should stop stealing this talk.
It's clearly compatible, right? I mean, there's a lot of steps, like 14 days worth of steps to make that connection.
That is very true, but we have more questions too, yeah.
Yes. So I actually planning to take that one. I'm getting a lot of pushback from people
who think I'm an idiot.
No. You're an idiot, but they think that in the long term, formal models are becoming less and less popular in the field, and would not be strategic to just take one course about it if I'm not, for example, going to University of Rochester and getting the full training.
Yeah, I mean, I think that's a big question about what we do as social scientists. And I think a lot of the way the field has gone in terms of thinking about causal inference and big data and so on, call into question what we do with formal models. And I think that those impulses are unhelpful and misguided. The enterprise here really is to think about causal explanations, identifying causes and being able to talk about them, and not estimating effects. And there's lots of good philosophical, right? Oh my God, philosophical reasons for thinking that just estimating effects is the wrong way to go. So part of this, I said, the people whose names I put up there are my friends and former students and colleagues. This is a lesson, I think, generally about this, and this program. Every one of these courses is going to raise debates and conflicts and disagreements among people who do this kind of work. And so part of what I try to do is put the disagreements out there on the table and help you figure out what you think right now about those things.
Very cool, very cool. Thank you very much. And Bob Lupton is next. And there you are. There. Yep, I think. And you can click with that if you like. And there's your mic.
Okay. I have to click on that. So I click in right about there. This one. Lefty's
If
backwards.
you haven't snuck off yet,
There we go.
There's no line.
Okay.
All right, Bob's talking.
Hello, everybody. Bob Lupton. I don't know what Jim was talking about, some words about Manchester and different places. I'm from the University of Connecticut. It's a two-time reigning college basketball national champions. I'm a political scientist over there. And I teach this course, Maximum Likelihood Estimation 1, Generalized Linear Models. It is a mouthful, and that's okay, because I'm going to be briefer than the course title suggests today. And it is an important course. So what is maximum likelihood and what is it good for? Absolutely a lot. So specifically, maximum likelihood is a method, statistical methodology for estimating quantities of interest we care about. Parameters, specifically, we're going to use a statistical method for given some data, right? Maximize the likelihood that some parameters produce the observed data, right? So why do we use that? Because it is a consistent and flexible method for estimating these quantities of interest, right? Maximizing the values that are most likely to produce the data we observe. When important assumptions of other models, namely OLS, Tim, love you in your course, but sometimes OLS is not, in fact, the right model to use, even though some people will tell you that you can just go right on specifying linear probability models for everything. We're going to helpfully disagree for that.
they're wrong.
Yeah, they're wrong. Thank you. See, and Rob's smarter than me. That's why they pay him the big bucks. They're wrong. So what we learned specifically, right? So we're going to apply maximum likelihood, right? Use it for models for which OLS assumptions are violated. Specifically, we start out with binary dependent variables, right? Simple logits and probits. Regression models, right? So 0-1 variables. Did people turn out to vote? Did a country engage in a war in a year or not? Did someone smartly enroll in MLE or not? And what were the consequences of that? And then we move on to different and more elaborate classes of models, right? Data that are ordered or group continuous data, and then a suite of models, multinomial choice models, right? And then we get into models where individual choice or decision making might vary across individuals and the choice. Right? We'll talk about bivariate, multivariate probit. We will also work with mixed logit, and then close with some multi-level models. It would be complementary to regression too, in the sense that they build nicely off each other, right? So we'll spend some time in this course at the outset just reviewing assumptions of the linear model and why we might move on from it in this course. Right? And so what will be the usefulness of the course? Quite a bit. I could barely sum it up in 10 minutes. But broadly, right, you're going to improve your toolkit for conducting statistical and data analysis, right? You're going to bolster your coding acumen and also improve statistical graphic skills, right? So all course materials and code and example and homework data will be presented in Stata and R. We will help you to the best we can with other software packages you might employ, but we'll have everything in Stata R available to you, right? So you'll have every lecture note ahead of time. You'll have homework, code, answer keys, and example answer keys, everything you need. Everything I present in this course, you'll have access to, right? We're an open book. We want you to learn this material and be able to apply it in your own work, right? That's the goal. We want you to be able to use these methods in your dissertation, in your published work, in your professional lives. If you are in the private sector, right, for business, actually use the skills to make money, unlike a college professor. And so we hope it's going to be a flexible and consistent estimator for a range of techniques and methods that remain extremely popular in the social sciences in professional work. But will we have a good time? Well, hell yeah. It's, life's too short not to have fun. The course is 8:30 a.m. to 12, but that's fine because I'm a one-man statistics electric factory. And so it's going to be a good time. And I hope that you, as you participate in the course in person or virtually or asynchronously, will also be energetic. I'll have daily ops hours just like everybody else and by appointment, right? We're here to talk statistics, right? The year is broken up into football season, the ICPSR, and then everything else we just is passing time. So we really look forward to this 3 weeks. It's going to be awesome. And we're going to have, by the way, there are 4 assignments that hopefully you'll complete as the course goes on, and then myriad other examples. A lot of it's political science and voting behavior, because that's what I study, but we have a range of examples, try to work in from other subfields in political science, from economics. We have health data, some sociological examples, things like that, to try to broaden our application of this methodology. So with that, I hope you'll like the course and enroll in it, and let's have a great summer.
Wait, are there any other questions for Bob before he gets back to the sweets table?
Oh, yeah, sorry, I was trying to get a brownie, can you believe it?
Yeah. Okay, well, if not, applaud for him again because he was that good. I'm trying, yeah, are you up? I believe you are. Adam Enders with measurement. And yes, indeed, you are number 6. And there you are. You can use that if you like. There's your mic.
Okay, I'm Adam Enders. I'm an associate professor of political science at the University of Louisville, and I teach the measurement scaling and dimensional analysis course with my 2 excellent TAs, Richard Kornrumpf, Halal Al-Zabidi. So everybody here is pretty much a social scientist, or just about everybody is, of some sort. How many in the room, just by show of hands, have ever had a course on how to actually go about measuring social science variables? So for the people online, more or less crickets, maybe 5 or 6. That strikes me as deeply problematic, right? Especially if you look at many of the big debates, the big sort of sources of conflict in each of your subdisciplines and fields. A lot of them revolve around how something got measured, right? So usually the way things go in even really good graduate programs is there's some kind of required graduate programming on an intro to political philosophy or an intro to research design or something along those lines, right? Where maybe you spend a day and you talk about, hey, these things like reliability and validity are important, right? And maybe you read a little textbook and it has this target thing, right? And the metaphor is always, if you can keep hitting the target at the same spot, that's reliable. And if you can actually sort of get it, in the bullseye, that's valid. And then it's like next chapter, right? That's nice. So somehow magically go make sure that you do that. That's not good enough, right? And my course is all about how to take measurement seriously and do that much, much better than just sort of guessing. So the course is called Measurement Scaling and Dimensional Analysis. So what does this word scaling really get at? Scaling models are sort of a broad family of methods designed to locate and isolate principal sources of variation among a set of variables and meaningfully translate qualitative observations to a quantitative metric. So the first few days of class are going to be actually thinking about measurement theory. It turns out there are folks that think about this systematically, right? Beyond just, here are definitions of validity and reliability. So we're going to think about what we actually do when we do measurement and how we could go about meaningfully taking something that's qualitative and assigning numbers to the characteristics of that object, right? And of course, along the way, we're going to end up with measurements that are more valid and more reliable than if we did so by guessing, or if we did so merely by sort of mimicking what other people do, right? It would be easy to see, oh, well, people report this little alpha thing sometimes next to variables in a paper, so I guess I'll do that. Also not a great strategy. So all of the methods are designed to do that at their core. In addition to producing better measures of the constructs that we're interested in, which, by the way, something not working well? We're getting some echo. You're working on it, Frank? Some echo? Oh, okay. Sorry about that. In addition to producing better measurements, there are some other things that this broad sort of family of methods does. So one is helping assess the dimensionality of the information we're looking at. So what are the sort of primary sources of variability? Let's say that I've got a set of 5 survey questions that are designed to measure psychopathy or something like that. Are they actually seemingly tapping into one single construct or a bunch of different constructs? Relatedly, data reduction. So can I take this broad set of variables and somehow distill it down into something that is actually manageable? So in this sort of sense, this course works really well as a precursor to like a machine learning class. Professor Hare, who teaches the machine learning class, would call this class basically supervised machine learning, whereas his is more like unsupervised machine learning. So that data reduction and prediction that goes along with it is an important sort of part of the course. And then also statistical graphics. So a useful thing about a lot of scaling models is they were sort of developed by these researchers that were interested in producing geometric representations of observations and thinking about things that way. And that means that we can draw nice pictures of things, right? It also means that when we're learning about these methods, we can do so, using words and using substantive examples, using math, and using some geometry and other kinds of visualizations. So a couple of examples of things that my course can help you do. So let's say you've got a bunch of survey items and you want to make a new variable. Maybe you've got a bunch of attitudes about policy spending and you want to use that to estimate ideology. The methods that we look at in my course will help you do that. Let's say that you want to decipher how many dimensions there are to some kind of phenomenon. My course can help you do that. Maybe you want to have better confidence that a null result is due to the model or due to a theory rather than inappropriate measurement, right? So we take all of these classes that are about modeling causal or not so causal effects between X and Y, right? And we can achieve all sorts of different results that have nothing to do with theoretically whether X and Y are related, but poor measurement of X or Y that corrupt, right, that bias our estimation of that effect. So you'll be able to answer all of these questions by the end of the course. Methods covered include a bunch of different methods for assessing reliability and thinking about validity. We start with simple kind of unidimensional models, the summated rating scale, kind of what a lot of people do and a lot of work, taking an average or something like that. We look at parametric and non-parametric item response theory models, exploratory and confirmatory factor analysis, although we don't go deeper into structural equation modeling than confirmatory factor analysis, principal components analysis, and then we'll end with a little bit of multidimensional scaling, depending on how things go. Along the way, we'll talk about measurement invariance. So is a scale measuring the same thing in the same way for group A and group B? We'll talk about scale development. So how do you go about actually developing a scale of survey items or something along those lines? And then nonlinear variants of some of the other models that I mentioned. Ideally, one would be very familiar with the linear model with OLS, beyond merely typing like reg into Stata. Ideally, but that's the way it is sometimes. Ideally, one would have a little bit of a notion of maximum likelihood estimation and some familiarity with R. I present everything in R in class, although I can consult when it comes to I can consult when it comes to Stata and some other programs, as can my teaching assistants. We'll have 4 or 5 homework assignments, sort of depending. They're all designed to be very sort of practical and applied. It's a real data set. I say, this is a question that somebody else has asked in some literature. Here's the data. Can you go about figuring it out? So it's very much designed to help you implement and actually have to sort of like speak about these methods, right? Interpret what you're actually doing in a sort of sophisticated way. Yeah, we'll have office hours every day. Plenty of exercises inside of class and outside of class for you to practice. And I think that's all I have to say. Sorry about the echo. I guess this is
Questions
a
from the
bad
room?
part of the room. Okay,
Any more? All right, Adam, thank you.
cool.
Sarah, I think you're up. Where's? Oh, that's right. Sarah is online, perhaps. Let's see. Stephanie, if you see, are you in the Zoom room? Can you see if Sarah's in the participant list? And if she is, can you promote her? Go on. Oh, she's got, oh, that's right. Right. Yes. Answering the question in the chat, that last course was called Measurement Methods for Scaling and Dimensional Reduction, something of that nature. Thank you. Stephanie answered exactly. All right, I have our next presentation about to call up. No, I do have Sarah Tomic and then you, right?
I was going to tell you, I have a website presentation. It's on the, all I need is a web browser.
Okay.
Yeah, we seem to be a web. So.
Okay, we got it. Yeah. All right, and
Hi, my name is Sarah Tomic. I am a professor at Baylor University, and I'll be teaching advanced multivariate statistical methods for the next 3 weeks. This is my 4th year teaching at ICPSR, and I look forward to doing it again. So let me talk a little bit about the course and the way it's set up. So what I like to think of as this is kind of the bridge between univariate techniques and moving to more complex relationships with multivariates, multiple variables. I guess when we think about multivariate, that's multiple variables. And really it starts with understanding how we move from one dependent variable to multiple dependent variables and how that affects our analysis and the relationships that you're looking at. So I think this is a really great segue to understanding more complicated techniques and more complicated techniques. So this is a great way to look at it. So how I kind of set up this course is you'll see the topics. I'm going to first go through linear algebra and how it's worked. We will deal with matrices since we're looking at multiple variables simultaneously. Then for every topic that we look at, I will move from univariate to multivariate and how they differentiate from each other. So you don't need to necessarily know everything about univariate statistics in order for them to next understand the multivariate. So you'll get a refresher of that. So first we'll talk about univariate normality and then how relationships change in a multivariate space and how we look at it. So moving to that, multivariate ANOVA, where we have multiple dependent measures, and then some of the other things we'll look at: discriminant analysis, cluster analysis, multivariate regression, canonical correlations, principal component analysis, and we'll get to factor analysis and how that works in more complex relationships. When I think about this course, the majority of the course, if I just want to boil it down to something, it is linear combinations. How we can take complicated sets of data that have multiple variables and make it easier to understand. So we do that through the use of linear combinations of variables so that we can describe one variable that is comprised of multiple variables rather than trying to understand all the variables independently. So using the idea of how we can take complicated relationships, turn them into more like sub-relationships when we think about it, through data dimension reduction by linear combinations. So if you're taking this class for credit, then I basically give you 4 homework assignments and a final. So each of the homework assignments, you get about 1 problem for each chapter that we go over. So if you look at it, you'll see that we have multiple, we basically do almost a chapter a day. You know, it's kind of tough, but for each chapter, we will, again, start with univariate, move to multivariate, how it changes. Then there will be some time where I show you how to do the analysis in R. We'll use R primarily for the course, and then interpretation of results and how to write up results in APA format. So I move through the entire progression of the data analysis, how we get from univariate space to multivariate space to actually analyzing and interpreting the data. So while it's fast, you will have all the materials. I have actually pre-recorded R videos as well, so that if you forget something that I'm going over in class and don't want to watch the whole lecture again, I have that as well. So I have the R code for everything. So again, I think that if you're interested in more complex techniques and want to learn more about how we analyze relationships between multiple sets of variables, this will be a great class for you. Okay, hope to see you, a bunch of you tomorrow. Thanks.
Next up, we have Dave Armstrong as he's getting ready for his advanced regression or beyond regression course, perhaps we should call it. And if we click there, I'll let you full screen it, do your do, whatever.
I have to share this on Zoom, Rob?
Should be, yep, you're good.
That's good. Okay, great. Welcome, everybody. Thanks. My name's Dave Armstrong. I'm a political scientist at the University of Western Ontario. I study comparative politics and methods. I did my PhD at the University of Maryland, and I write, if you look at my CV, about all kinds of things, but they mostly revolve around conflict or voting behavior or local government. I've been here 24 years, starting as a participant in 2001, and then a TA for a while. And then I've been teaching various things here for almost 20 years. So our course is really about robustness. All of the techniques that we talk about and things we discuss will really revolve around the idea of understanding whether a model or a result or an effect is robust or not. And the first thing we have to do when we do that is conceptualize this idea of robustness. And we're going to start, and this is going to guide our entire investigation around Eric Neumeyer and Thomas Plumper's book, where they talk about robustness really as stability. We'll talk about what other ideas might pop up when we think about robustness, but we're going to focus mostly on this one. And it was interesting, when Tim was up earlier, I had the great pleasure of TAing for Tim when I was a much younger person. And so I may have picked some stuff up from him as well. So we'll tend to talk about things in words and math and pictures, and hopefully one or some of those things will resonate with folks. And so when Neumeyer and Plumper talk about stability, what they're really talking about is the proportion of a robustness results effect that is in the 95% confidence interval of a baseline model's effect. And so in math, it looks like this, which maybe looks kind of scary. But really all we're trying to do is this, figure out between 2 bounds how much of a distribution falls in between them. And luckily for us, most of the times the functional form of the distributions are already known. Usually it's normal for the things that we're talking about. And so that complicated equation is actually pretty easy for us to solve with software. We'll talk about the 4 steps of robustness testing. So defining a baseline model, identifying what kind of arbitrary modeling choices and assumptions we might have made, and then developing models to try to change those assumptions in useful ways. And finally, thinking about what does robustness mean for these alternative models. There are several types of robustness tests, really broad strokes. What Plumper, Neumeyer and Plumper talk about are really tests against plausible alternatives. So how does my model or my effect or prediction or whatever I'm evaluating stack up against models that are good plausible alternatives to that? So other good ways that are sort of consistent with our theory that we might think about those effects. They also talk about a set of tests against mostly implausible alternatives. So how far would we have to push our result to generate a non-result or a sort of counterintuitive result? And does that limit happen within a set of reasonable alternatives, or is it actually outside the set of reasonable alternatives that we might have? I thought I'd just show you a couple of examples here. I thought I would pick on my own work rather than trying to pick on somebody else's work. So I've got a paper with a grad student where we talk about the effect of demographics. Oh, this didn't show the first one. Demographics and personality traits on Green Party support. And we think those effects are mediated through environmental attitudes. And so we developed a baseline model. We developed, and in this particular case, we had multiply imputed the data because there were a bunch of missing values. And so one of the things the reviewers said were, well, I'm not sure I really like those imputations. Maybe you should tell me how it works with the listwise deleted model. And while I was sort of loath to do that, I did it anyways because that's how you get papers published. But this conceptualization of robustness gives us a really useful way of thinking about how close are those results, right? Oftentimes when somebody asks, and in fact, if you look at the paper, we didn't do this. We did the thing that people usually do, which is we estimated both models and they looked kind of the same. And so we just asserted that the model was robust to imputation because the effects were kind of similar. This gives us a way to really characterize how similar those results are or how stable those results are with a continuous measure of robustness. I also, so here's another example. This paper came out of a class that I took here when I was a participant, so it's kind of old, but we talked about the effect that democracy has on state repression, and we hypothesized that there was kind of a threshold that happened on Polity's democracy measure around 8, so it ranges from 0 to 10. And so one of the arbitrary decisions that we made, are theoretically derived, but arbitrary nonetheless, is that the cut happens at 10, so the effect or at 8, so the effect changes not so much direction, but certainly magnitude at 8. And so we might wonder, well, how robust are our predictions from that model to that particular cut point? And the answer is really not very. That cut point's doing a lot of heavy lifting in this model, and if we change it one direction or the other, some of the values or the robustness of some of the predictions that we make, particularly for democracy in the kind of low middle ranges, really suffer. Does this mean our model's bad? Well, not necessarily. It just means that the choices that we're making have a real effect on what we're finding. And as long as we can justify those choices, that makes sense. But now we actually know how robust that result is across a wide range of alternatives, right? So those are the kinds of things that we can think about. But there will no doubt be all kinds of other things that we could talk about as well. We'll also talk about comparing this conceptualization of robustness to others. Neumeyer and Plumper talk a lot about lemur sensitivity analysis, which might not mean anything to you, but it's a thing that probably all of us have done, which is we estimate a bunch of models and we say that the sign and significance of the thing I care about is the same across all the other models, and therefore I did a really good job estimating my model. So we'll talk about that and some other alternatives as well. One of the things, I mean, you might wonder, well, how can we do a whole course about this relatively simple idea? And the way is by talking about all kinds of different models and how we can use these models to probe robustness across a wide range of choices that we might make. So we'll talk about generalized linear models, nonlinear and conditional relationships, so thinking about polynomials and regression splines. We'll talk about generalized additive models, which again allow us a more flexible set of functional forms. Supervised machine learning models like multivariate adaptive regression splines and random forests. Doubly robust estimators, which are kind of all the rage now. We'll talk about bootstrapping, jackknifing, and cross-validation, so different kinds of resampling techniques that can be useful. Robust standard errors, we'll talk about robust regression. I mean, it's got robustness right in the name, so we probably ought to talk about those things. And multiple imputation. So we'll cover a really wide range of techniques, but all kind of in service to understanding how robust a result is in a baseline model that you specify. And that's going to be the glue that holds all of these disparate techniques together. As for the audience, it's pretty much anybody who wants to know whether their model effects are robust or not. If you're happy with blissful ignorance, that's fine. You can take other courses. But if you want to know or think about how robust your model effects are, that's what we're going to do. In terms of background, for stats, a familiarity with the linear model is pretty much required, and a sort of passing familiarity with GLMs would be great, although not necessary. Familiarity with R would be good because we're going to do all of the computing in R. It's one place that does all of the models that we're going to talk about. There are other places that do some subset of these models. Or there are other software that do all of these things that I don't know. And so we're going to do all of this in R. And for math, if you had a sort of intuition behind how the linear algebra and derivatives and integrals work, in the sense that if I put one up on the board, you have some vague notion of what it's doing. We certainly don't need to solve them out by hand or anything. But if you have an idea of what they're doing or what's going on, what I mean when I put it up, that would be great. In terms of assignments, there'll be probably 3 assignments. They're very applied, mostly thinking about applying the tools that we've done in software to a real data problem that you can work through and think about. So with that, I'll be done. Thanks.
We have a question on the Zoom. How much review is done in the course? If I'm taking regression 2 as well, would you say it makes sense to take these courses simultaneously?
I guess it would depend on why you're taking regression 2. If you're taking regression 2 as mostly review, I think it could make sense to do these simultaneously. If you're taking regression 2 because it's new material, taking that course and this course at the same time is probably not a great idea. The stuff you talk about in regression 2 is foundational for what we do in the class, so probably not.
That would be a perfect opportunity to backpack Dave's advanced regression and take 2 now and Dave's course later. Other
Absolutely.
questions here from the audience or on Zoom? There's one over there, Dave.
Yep. Yeah, I think that would be fine.
The question was?
Oh, can you use your own data for assignments? As long as it sort of fits in with the context of the problem. I mean, there may be things where a particular set of data might not. There might be things we'd be asking you to do that don't really fit, but so long as they do, I think that would probably be fine.
Yeah. All righty.
Okay, thanks.
Yep, thank you. Stay. And Justin, Justin, are you up next? Where's my list? Yeah, shouldn't I know? Is that what you're going to say? Where did my list go? I had it open in a certain window. Anyway, you're next by fiat, Justin, since we have you. Maybe just, yeah, there you go. And you are next. So next up is Justin Esseret to talk about Bayesian modeling for the social sciences. I think you're good.
All right. Hi, everyone. My name is Justin Esseret. I'm a professor at Wake Forest. I'm teaching Bayesian Methods 1. This is a 2-course sequence that the first part is during the first session, the second part is during the second session. So welcome to summer and to ICPSR and Bayesian Methods 1. I hope you'll all get a chance to take my class. Why should you take my class and not those other terrible classes you've been hearing about up till now? Well, you will learn important skills. One thing you'll do, although the second course is more focused on theory and ours is more focused on practical sort of getting your running with Bayesian methods, we will learn some Bayesian theory and epistemology, including a little introduction to Bayesian process tracing. And just so you can see, Bayesian process tracing is a way of using the logic of Bayesian inference and applying it to arbitrary kinds of evidence, including qualitative evidence. This is an app that I've been developing in sort of connection with a paper that's related to it. By the way, if you want to see any of this stuff, the slideshow and everything I'm showing you is at my name, justinessery.com/ICPSR. So you can follow along at home or whatever. But anyway, so one thing we'll be doing is talking about how to apply Bayesian inference to sort of problems that aren't necessarily purely quantitative, which is possible. You go out here and back to there. You'll be learning how to create reproducible analyses in R and R Markdown. So there are 5 homework assignments in the course. They all involve creating R Markdown documents that produce some sort of analysis replicably. This is actually from the very first homework that is assigned. Sorry, it's a screenshot, so it looks like crap. I assure you it looks great when you see it in PDF. But all the code, all the analysis, and actually even the answers to the problem are sort of all integrated into one thing. This is just sort of part of what we teach as part of the process. Probably could even be its own course, but we do enough there that I would say that's a benefit of doing it, taking our course. You'll be conducting analysis using the most common software packages for Bayesian analysis, including STAN, which is Andrew Gelman's thing, and JAGS, which is kind of everybody's thing, I guess Martin Plummer's thing maybe. So this is an output of one of the first or second assignments, analysis in JAGS. This is an MCMC plot, a trace plot, and then the sort of inference distributions from 4 different chains. And then finally, you will learn how to create visualizations of these results using ggplot2 that will also carry over to lots of other things you're probably going to be doing. So this is a cool little GG ridges plot that comes out of a Bayesian analysis, looking at the I think this is like the extent to which GDP per capita has increased year over year over time. I think this is actually a model product. So there's an initial increase and then a sort of reversion to the mean. So for all that and more, come see me. The course starts tomorrow. It runs throughout the entire first session, 1:30 to 5:30 p.m. Mason Hall 1427 or online via Zoom web conference. And I know some people have been talking about sort of prerequisites. It's I kind of think this is implicit, but you probably shouldn't be jumping into Bayesian methods unless you've taken at least a regression course and perhaps a little bit beyond. GLM is very helpful if you've already taken that, although it's probably possible to do it without GLM. And the other thing is some degree of familiarity with R and R Markdown is helpful. We're going to teach a lot of that, but the more that you bring with you, the easier time you'll probably have. That's it. Any questions? Yes.
Yes, this one. So when I saw it, I was curious, is this a simulation? So is the work based on empirical data? observational data, or because this for me sounds interesting. So I don't know what kind of data are you gonna use, right?
The answer to your question is the simulation, or is the course, does the course use simulation or does it use empirical data? The answer is yes, it uses both. First of all, Bayesian methodology, although it doesn't actually have to be, in practice almost always is based on some kind of simulation-based method. And in fact, the first part of the course is just teaching people how to think computationally, right? Don't solve your problems with theorems. Solve your problems by programming whatever the problem is into the computer and then let it tell you the answer. There are some problems that are sort of pure simulation. Actually, this is not really much of a Bayesian methods problem. Like, this is just a pure simulation problem. But most of the examples, especially once we get into teaching the real heart of how do you run a Bayesian model, how do you interpret it, how do you diagnose it, how do you tune it, those are all those examples are based on empirical data for the most part. But there is a strong component of computational thinking that's kind of unavoidable. And so we just teach it. Other questions? All right. Thank you.
Just continuing the theme we were talking about earlier, theorize your models. You can then build it into a likelihood, since the outcomes we care about are probabilities, other random variables.
We can't.
Can hear you.
Thank you for shouting that in to interrupt me while I was on. I was saying, like we were saying earlier, when Jim Johnson was on, you could theorize your models about the processes you care about, the outcomes you care about, and produce systematic logical propositions about it, as well as how it works. You could then build that data generating process into a likelihood. That is, these outcomes we care about. Oh, are you kidding? These outcomes that we care about are random variables, right? So that means they have probability distributions. That means you can write those probability distributions as the result of theoretical arguments to use data to maximize the likelihood in order to estimate how that process works. And then if you go Bayesian, you can get even richer with this. You can add all sorts of propositions and parts of the analysis that are uncertain. Perhaps you have a measurement concern that you're interested in tackling. The ideal way to do that would be to build that measurement model into the empirical analysis rather than do it separately. And the best way to do that would be with the Bayesian course. So if you can manage, keep coming back. Take every one of these courses, including this next one, which, well, that would have been better if I could have said it smoothly. Including this next one, which is, that was, so the next one should be Ben Hansen.
There we go, that's much better. All right, so I was saying that I'm a professional statistician rather than a social scientist. I want to connect that a little bit to the other thing in the title of the slide and the title of the course, Causal Inference. Earlier in the discussion of other courses, you heard the contrast between causal explanation and causal measurement. This course is going to be much more, of course, about causal measurement, which is something that increasingly social scientists have found an important role for in their work, although not always the number one tool. My co-instructor Tom Levitt, who's taking over in the second part of the course, is a social scientist, although he's over his years as a first TA for this course and a co-instructor of this course, he's been able to imbibe the mathematical perspective sufficiently to a point that in 2023, he was presenting at one of the leading stats conferences on causal inference. So there's a lot of interest in our side, on the statistician side, about what's happening in social sciences. And part of what we're doing in this course is building bridges between those things. We have two TAs for the course, Moda and Abdullah, who are also graduate students in social science disciplines. I'll just mention that Abdullah, the one of them, a student at the University of Illinois, has taken classes with another instructor of this course who's co-developed our materials. That's Jake Bowers. He's not teaching it this term, but Jake is sort of lurking in the background. We've, over the years, developed the course together, Jake, Tom, and me. I said I was going to talk about causal inference and causal measurement and stuff. Let me do that in the context of introducing you to the course outline and how we're going to go about looking at introducing these topics. The first thing that we spend the bulk of the first week of the course on is the randomized experimental ideal. In a way, this is setting us up for the idea that in this course and in this part of applied statistics and medical and social science, frequently what we're doing is we are theorizing the measurement process as opposed to theorizing something else out there in the world, because this gives us a more modular approach to drawing causal inferences and making inferences about what causal effects may have been. The important conceptual elements of that are the randomization distribution that occurs in randomized studies and potential outcomes. And what one can do with those things is make inference about whether causation occurred and estimation about the extent of causal effects in fully controlled randomized experiments. This part of the field was developed essentially starting about 100 years ago by Fisher and by Neyman, two very important figures in the field of statistics who, for the better part of the 20th century, were known for contributions other than these in causal inference. Really, each of them dabbled in this in different ways. At the beginning of their careers in the 20s and 30s, they fought bitterly amongst each other, and partly as a result, their work sort of lingered in subfields and didn't come to the mainstream of stats or anything else. But there were important developments during that time. Again, mostly in these subfields, many of them more oriented towards medical science than social science. But it was in the 80s and 90s that the importance of these kinds of ideas, the potential for clarifying issues that otherwise tended to be very, very murky in studies of the social world, came into focus. And that aligns with our transition in the course to part 2, where we look at imperfectly controlled randomized experiments and see how it is the conceptual apparatus one develops for understanding this experimental ideal thing is helpful for making persuasive studies around things that aren't quite perfect, the common imperfections that arise in practice. In a similar sort of spirit, the methods get applied to non-randomized studies where, in practice, researchers have no control over the parts of the measurement process that are most important from a statistical perspective. But it has proved helpful in a number of areas to theorize those things. The theories, the style of theory that comes up around them is at its, that happens in a bunch of places in stats. It's at its clearest in matching studies, as well as arguably difference in differences studies and regressionist continuity studies. So we're going to look at those things in part 3. This will be, at this point in the course, we'll be into the part of the course that is more squarely in Tom's wheelhouse than mine. Also in part 4, we're looking at omitted variable sensitivity analysis. And these are the methods that statisticians and others have developed, recognizing that when one's working on with the sort of theory that isn't buttressed with strong control of the measurement process. There's a need to study the robustness of one's techniques, and this is the specific style of that study that has evolved in tandem with the methods we will have been studying up to that point. So that's our outline for what we do. This part 1 of the course is a very conceptual piece, and when I say that statisticians and others working in this tradition like to theorize the measurement process, another way of getting at that, the more common jargon to hear in the causal inference subfield is randomization or design-based inference. Randomization-based inference being keyed to strictly randomized studies, design-based inference being something that's a bit broader. So we start with this part of the course. It is often the most challenging for students in the ICPSR course. And I think that's because that's the part of the course that is the strongest reflection of these sorts of ideas that statisticians, largely not entirely mathematical statisticians, but statisticians developed and were sort of developing on their own in the dark with less engagement with the rest of academia. It's not that there is a lot of mathematical prerequisite. In fact, there isn't. There's relatively little mathematical prerequisite to this course, but there is a need to acquaint oneself with a style of thinking that probably comes a bit more naturally to mathematicians than to others. So I've gotten a lot of help from Tom and from Jake Bowers over the years in helping to improve this first part of the course so that people can get more out of it. There's a bit of computation in the first part of the course because this field actually, although in its substance is kind of, we'll be emphasizing things that are probably rather different than you would see emphasized in a Bayesian stats course. A lot of it nowadays works the same way in the sense that if you really want to understand what's happening, it's helpful to implement it in computing and look at the computational experiment. And many of the relevant theorems, in fact, aim to emulate and tell you what would happen if you were to do that. So we'll do some explicit computation as well as conceptual exercises oriented to that in this first part of the course. There'll be an emphasis on computation in R later in the course. OpMatch, the OpMatch package that I've been involved with developing is one important piece of that, but not all. So I wanted to tell you a bit about the course goals. It may be that, our marching orders were to do some marketing and to sell you on our course. At this point, I want to do more marketing than sell you on the course, which is to say, help you understand whether this is aligned with your needs or whether something else is. One way of seeing that, if the sort of broader conceptual stuff I was saying, one way of seeing whether this aligns with your needs in research is to take a look at the methods we're going to be studying. There certainly have come to be fields and subfields where it's absolutely essential to understand what's going on with these sorts of methods. And if that's you, then I hope you'll take a good look at the course. Randomization and based analysis for experiments, and which goes hand in hand with design-based analysis for quasi-experimental studies. We'll be looking at instrumental variables and principal stratification, which conceptually relates to the idea of mediation, but it signals a different methodological tack into the same measurement challenges than you would ordinarily get when people talk about mediation models. Propensity scores and propensity score matching, as mentioned on the last slide, are an important piece of this, as is omitted variable sensitivity analysis. And the way we're organizing instruction is with an aim to set you up to unpack and make sense of your own and others' research projects in these sorts of causal inference terms, to recognize modules or potential modules of a research enterprise that could consist of activities aimed at causal measurement in the surface of other things. We want to set you up to understand a suite of valuable research designs, both experimental and observational. And we want to set you up to implement those sorts of statistical analysis and data collection, those sorts of designs, along with sense making of them, of the sort that you would need to publish papers on research you may conduct. So the course is pitched at the applied scientist who plans to use causal inference in their research. We don't have a whole lot of mathematical prerequisite I mentioned, but it is helpful to come with some prior exposure to R. If you have no prior exposure to R, then there's a bigger chance you'll be learning that and some of these other things all at once. It makes it more difficult. We assume some familiarity with statistical concepts, such as random variables, expected value, distribution functions, and the like. The underpinnings of regression techniques, such as maximum likelihood, those sorts of things play a much lesser role, if any, in this course. When I say these familiarity with statistical concepts is assumed, I would think that if you come to it with a lot of background in R, but relatively less background in those specific things that are mentioned here, or the converse, then it's likely that we can work with you. You can have a good experience in our course.
Yes, question back.
Quick question on, for those who take this course with the hope that it could reflect grade in their own institutions, what would be the expectations for assignments and stuff?
Oh, yeah, okay, great, I should, thank you. So I should keep assignments for people
who want to do great and just people who want to follow on with the course in the intended manner. We'll be doing some exercises and things in class. In addition to that, there'll be a weekly assignment, some of which builds on what will have happened in class. And so we'll wind up with 3 of those. In the last of the 3, there's some opportunity for those of you who have a data set and some things that you want to engage with. There'll ordinarily be an opportunity to take that further in that. Thanks. Thanks for the question.
Can you just say which specific design-based methods they might learn in the course? GE, different. I think you started the list. What would be your list?
The word difference and difference nowadays encompasses a broad set of debates. We're not going to get into that whole set of debates, but in the course of the course, you'll get fixed on the basic ideas. So you'll get a chance of being able to enter on difference and differences. Certainly, matching designs will be a part of it. Regressionist continuity is on the time permitting list on this for this year. We have material on it. We'd like to talk about that. It may or may not be a bigger or smaller piece of the course. I did not put synthetic control on the slide. So I'm not going to talk about synthetic controls in my part of the course. It would be unsurprising to have that be a piece, but not a big piece of Tom's part of the course.
Is this one? Okay, great. So, hello everybody. My name is Robert Cooper. I teach at Dartmouth College normally, and I've been doing this workshop here for about 5 years. And I've been associated with ICPSR since about 2012. I'm going to take a slightly different tack, and I'm not going to tell you not to take the other classes, the other workshops. I'm going to tell you to take other methods workshops because they will go together very nicely with what my particular workshop is about, which is about communicating those findings, right? So data visualization. I would say that I learned how to teach at ICPSR. The reason why I would say that is because the ICPSR community is so diverse. And I don't need to go over all the dimensions. As you get to know everybody over the course of the workshop, you'll see exactly how diverse everybody is from backgrounds, origins, professional goals, other demographic characteristics, right? And so learning how to communicate effectively is really, really important in that context. And data visualization is nothing more than learning how to communicate your research findings as best as possible. So that's exactly what this is about. So why is DV actually important? Well, mostly because a lot of people are very busy and they might be too busy working in their own research to be able to read and understand and be compelled and moved by your own research. Some people may not care as much about research and statistical findings as we would like them to be. So it's not really a hostile argument, it's just a reality check, right? So how do we get the public's attention? How do we get other researchers' attention in this context? If it's really possible at all, we take a few keywords and best possible graphics to distill and communicate the data story. And really, the first stop for that is these days is social media, right? So usually you have a few words, you have a couple of visualizations, and that's what you have in order to communicate your story and say, this is what I'm doing research on, this is why it's important, and this is why you should care. First and last impressions are in fact everything. Data visualization brings with it all the stuff that you have to do when you're engaging in research anyway. Because it is really the end of a long process of reduction, where you're finding sort of phenomena in the universe that you wish to study. You're going from there to finding measurable dimensions, and we've had people talk about measurement again here. Collect the data, reduce the data to some sort of data analysis, reduce your analysis to components worthy of attention, and turn those into visualizations that people might actually be compelled by, right? So data visualization is sort of, if you're using the analogy of the iceberg, it's just that tip of the iceberg that you see at the end of the result. Everything else, that entire arc of the story of your research is everything under the water, right? So data visualization isn't one skill, it's just a large skill set. So again, I say my class is sort of best in context with other methods courses, right? To adapt a quote from John Tukey in DV, very little attention will be paid to the actual methods used to attain the results of our analyses, because there are lots of other good ICPSR workshops that do just that, right? Take those workshops, get your findings, work with your data, come to data visualization, and we will figure out exactly what's the appropriate visualization with a set of most compelling visualizations that might be good for your research. Based on our descriptive or inferential statistics, we'll kind of take sound statistical methodology as a given. Based on our descriptive or visual or inferential stats, then we will match our data to appropriate graphics that are not only scientifically correct, but also story maximizing and compelling. Okay. So what will we do? The software and the classes are in our studio. We'll learn to work with our raw data. So the first week of the class is almost all data work. There are very few plots actually that we'll work through in the first week. Then we'll start to actually get into the visualization component. We'll talk about principles of visualization. We'll get super nerdy about color theory. I'll talk a lot about plot customization and how to make things far more professional, interesting, and targeted to different audiences. And then toward the end, in the last week of class, we will work in some web scraping and some both static and dynamic web scraping. We'll work in interactive plots, animated plots, geospatial mapping, and then given time, we will at least dip our toe in the water of advanced data visualization, which really isn't quite enough time. 3 weeks isn't enough time to really get there, but we'll dip our toe in those waters at least by flashing outside of R and RStudio and getting into web technology. So we'll use JavaScript and sort of the D3.js library. So D3 is artisanal, bespoke visualizations, we'll say. You know, you can essentially, it might take you 50 lines of code to make the bar plot, but you can also invent a new visualization that didn't exist before, right? So that's the basic structure of the course. There are 3 assignments and 1 project. The project is where you get to actually take your own data, whatever research you're working on, and use what you've learned in the course and build your magnum opus visualization, build your 5th symphony, the best thing you've got based on what you learned, right? The 3 assignments are pretty code heavy, but again, the first one has nothing to do with plots. It's all about data work. It's the last 2 that are really about visualizations, and it gets pretty thick. So that's the basic structure of the course. That's all I have to say.
Here's what we're going to do.
We're going to go off screen. Keep working on that.
All right.
All right. You're plugged in. You're mic'd up. You can go anytime you're ready.
All right. Can everyone hear me?
Clay
Yes.
Webb.
Yes. Yes. I am Clay Webb, political scientist from the University of Kansas, and I've been teaching this time series class for 10 years. And before that, I was a TA for the time series sequence. So the introduction to time series and panel data analysis, you're going to apply statistical tools to time series and panel data. Time series data are chronological sequences of observations that are regularly and repeatedly measured, some characteristic of some phenomenon over time. So you've probably seen, if you've ever just turned on a television, seen a graph of the stock market, right? Dow Jones Industrial Average, what have you, you have seen a time series, okay? Quarterly United States consumer sentiment, monthly presidential approval. Panel data are just pooled time series. So you, instead of having one time series for one cross-section, you've got multiple cross-sections. And so instead of maybe having the Dow Jones Industrial Average as a time series, you could have the 30 firms that make up the Dow Jones Industrial Average and put those in a data set and analyze them. The same tools get used for both of them, right? So presidential approval as a political scientist, right? Our favorite time series. A single observation or single cross-section measured over multiple points in time, but panel data will be multiple time series in a data set. And they have the same basic structure. We use the same basic tools, but we have to deal with the heterogeneity that exists in the data and build that heterogeneity into our models. So why would you take this course? Well, do any of you study things that vary over time? Then this is an important course, okay? You would not look at a single piece of film and say that you understood the movie. You would not listen to a single note and say that you understood the opera. Why would you take a single cross-section of some dynamic phenomenon and think that you could understand the entirety of that data generating process, right? This is an essential part of your statistical education. And so you better show up at 8:30 tomorrow. Otherwise, all your models are going to be wrong. Static models are misspecified. Your estimates are going to be biased and inconsistent. Your standard errors are going to be incorrect. Your inferences are going to be misleading. And that's not just a matter of, oh no, we might have misled science because we rejected a null hypothesis when we weren't supposed to. The bigger problem that you're going to face is you're going to fail to reject the null hypothesis when you should have because you haven't specified the model correctly. Time series data also create new opportunities for inference. If you have a dynamic model, then you can make dynamic inferences. We can see how changes in X propagate into Y over time, and we can map that process. What does that look like? How does it change? With panel data, we can make comparisons across countries that were, or units, right? Like time series. I study international relations, so I'm always thinking about countries. My apologies. But comparisons across units, and if you have data measured over time, then you can relax the exogeneity assumptions that are typically required in regression models so that you can estimate models with multiple dependent variables using systems of equations. So this class is for everybody who studies things that vary over time. That's you, unless you're very boring. I don't know. Like, even mountain ranges change over time. It's just a matter of temporal aggregation. So you should be taking this class. But it's especially important for political scientists and economics. The primary focus of the class, though, will be hypothesis testing and statistical inference for the purpose of testing theories. So there's varieties of time series analysis that focus on forecasting. We're not going to be focusing on forecasting because it's not something we do very well in political science because we don't have very good data for it. We're not going to talk about spatial econometrics either. There's separate courses about that. But you can think of this class being prerequisite to those more advanced topics. The only thing that you need to bring to this class is a basic understanding of regression. If you've taken something that is akin to our Regression I class, if you understand that beta is a covariance divided by a variance, then you are set up for success in time series analysis because the majority of what we're going to be doing is using linear models. Hopefully you've taken some Stata and R, but we're going to have all the applications in both software programs. So we're going to have 11 lectures over 12 days. We begin with a sort of a reminder about regression and the things that you'll need to know later in the class, and an understanding of what we're getting wrong with regression models when we fail to account for the temporal dimension of our data. Then we're going to use dynamic ordinary least squares regression, including lags of X and Y in our models. We'll introduce panel data models, and then unit root and stationarity tests. So time series can sort of be stationary, have equilibrium that they return to, but certain time series don't have means that they return to over time. They tend to wander off in different directions. And we have a series of tests that allow us to arbitrate between stationary time series and non-stationary time series. Those tests end up being important because they determine the type of regression model that you're going to use. We're going to talk about co-integration and error correction models. So even if we have some phenomenon that is non-stationary, unpredictable by itself, it's possible that it, when combined with another unit root process, creates a stable equilibrium, and we'll learn how to model that. Then we'll have a hypothesis testing procedure developed by Susanna Lin, Matt Lebo, and myself that allows you to test hypotheses about long-run relationships when you are uncertain about whether or not your data are stationary or non-stationary. And then we'll sort of cap off that part of the course by talking about the varieties of exogeneity assumptions that end up being important for statistical analysis. There's not an exogeneity assumption. There are many exogeneity assumptions. And the exogeneity assumption you need to make depends on what you're going to do with your data. So we're going to introduce tools and tests and sort of theory to understand how we arbitrate between the varieties of exogeneity. And then we're going to relax that exogeneity assumption and use vector autoregression models when we have phenomena that are mutually constituted, okay? If you're walking, people are always walking around with feelings about the economy. We're here at the University of Michigan, right? All right, very nice. Feelings about the economy and feelings about the president in their head at the same time. So you can't treat attitudes about the economy as causally prior to attitudes about the president, and you can't treat attitudes about the president as causally prior to attitudes about the economy. So instead, we can build a dynamic system of equations to understand those relationships and how they work over time. Then we're going to get into an entire different approach to time series analysis. The Box-Jenkins methodology, ARIMA modeling, was initially developed as a forecasting tool, but can be used for hypothesis testing and statistical inference. We can decompose the variation in our data into autoregressive elements and moving average elements, and we can build those sort of filters to take all the features of our data that are non-random so we can focus on the interesting part of the variation in the data, the stuff that is random and related to our independent variables of interest. We'll talk about seasonality, advanced ARIMA topics, this, seasonality, fractional integration, and then the last day of class we'll talk about autoregressive conditional heteroscedasticity models, which is complicated sounding, but it's actually not too bad. Once you understand ARIMA models, an Arch-Garch model is just building a model of the variance of the time series rather than the mean of the time series. And we can test hypothesis about the variance of our time series the same way we would test hypothesis about the mean. And we have 5 homework assignments, I think. Yeah, and associated with each of these elements, and we'll have lots of applications in Stata and lots of examples to give you all the code you need to get through all of this and hopefully apply it to the data that you have access to. So I'm University of Kansas, Dominique Beta and Sun-Hee Kim from the University of Michigan and Texas A&M are my incredible TAs that I cannot wait to work with. And I hope that you show up at 8:30 tomorrow to learn about time series analysis for all time, always. Okay.
Time is an illusion, Clay. Time is an illusion. Machine learning. That's what'll get you right. Hi, I'm Chris Hare. I'm a political scientist at University of California, Davis, and I teach the machine learning workshop. What I really want to get across, I think, most with, right, this is such an enormous field. It's one that's so rapidly changing. It's one that's, I mean, we certainly live in interesting times. The way that I structure this workshop is from a social science perspective, right? It's meant for social scientists. It's rooted in social science and thinking about how we can adapt these cool technologies to the endeavor of social science, right? Rather than the reverse of remaking social science to fit the demands of these new kinds of methods. Okay, so what does this mean? Few things. One thing is technical, right? That the workflow of these processes is different, right? It's very foreign. It's a different culture. There's a classic article we talk about called The Two Cultures by Leo Bremen, who talked about the data modeling culture that most of us operate in or being trained in or have been trained in, and this new algorithmic culture. And it entails a new set of demands and workflow. So thinking about things very seriously, like the bias variance trade-off, right? That's really going to be central to everything that we do. And that's something that hopefully is familiar to you, but it's not something that is as front and center as it is with these kinds of methods. It's going to color most of everything that we do. So thinking about hyperparameter tuning, right? That's just sort of it's just different than what the way that our workflow usually proceeds with quantitative data analysis. The other set of considerations that's just different about machine learning, right? So there's this whole technical aspect, but also this raises all kinds of important but very tricky kinds of theoretical and philosophical kinds of questions about what is science, right? How does science proceed? What is our job? What is our goal in creating and building and testing models? And specifically differences from things that distinguish deductive learning from inductive learning, right? Learning from the data, letting the data speak for itself, and the myriad complications and controversies that arise from that. And so that's another big conceptual part of at least the way that I structure this workshop, right? This isn't a basket weaving class that we come in on day one and start making baskets. We kind of need to eat our vegetables a little bit to ingratiate ourselves in this culture and this different way of thinking, and specifically thinking about how this can be fit, these methods can be fit into the larger social science framework. Okay. That being said, right, that the focus is also on how do we use these methods in a very applied setting. So not a tremendous amount of math here in this course, and not tremendous amounts of focus on, well, there's gonna be more focus on conceptual aspects of these methods, but always with an eye, hopefully always with an eye towards applications, right? How do we actually fit this into the mold of what it is that we want to do, the social science questions that we actually care about, in a way that you don't always get that with machine learning workshops. You know, in a computer science presentation of machine learning, there's just going to be a very different set of emphases. Certainly not wrong, it's just that may or may not be so useful for us. The kinds of questions that we care about and the things that we want to do, there are strategies for working, for adapting machine learning methods to those demands, but we have to talk about those, of course, right? So things like bootstrapping to develop, to build our own confidence interval, or to get a test, or get a sense, I should say, of the robustness of the algorithm that we've built. We've spent a lot of time on interpretable machine learning, this really exciting subfield that for social scientists, right, this is first and foremost, right? One of the big frustrations with these methods is, well, okay, that's all well and good, but where's the regression coefficient, right? There's something very nice and tidy about that, and it has stars or it doesn't, and we get to do inference from that. These methods don't present as easily tidy results. That being said, we can crack open the black box, right? There are different strategies and experiments and simulations that we can do to get at least a sense of what's going on inside this magic black box algorithm that we've just trained. And of course, visualizing results, thinking about how to actually present and interpret ourselves what's going on in these algorithms. That's gonna be more of the focus. We start with method. I think a natural place to start is with adaptations, you know, kind of taking baby steps from adaptations of the basic regression model into this algorithmic machine learning kind of culture, right? So things like lasso or ridge regression that have a sense of the old, right? So hopefully there's some familiarity there that it's hard, it's a regression model, but we're gonna add some bells and whistles to it to make it more machine learning method is. So it's this kind of interesting hybrid. I think it's a good place to start. Spend a whole lot of time on tree-based methods, individual decision trees, but more prominently random forest, boosting-based methods. Still the best, still the tops with tabular data, which is most of our bread and butter. And so we focus most of the time on that. At the very end, we start getting into neural networks, deep learning, right? All of the potential that holds. We won't get to spend as much time on that because, again, this is much more of a social science presentation of machine learning methods. But we will get into it. We'll start talking about things like word embeddings, a little bit of large language models, transformer models, things like that. But I don't want to give the sense that we are able to go into great depth in that because we have 12 days, right? So that's, we definitely will get to it, but the amount of time we are able to spend on it, that's very much up in the air. Okay, as I've noted, right, this is designed for social scientists, and specifically those with some background in statistics. Hopefully you've taken a regression course, hopefully you're comfortable with regression. and you're ready to add this new set of tools into your toolbox. So yeah, you don't have to be math whiz. That's not expected. We're not going to do heavy math, much more focus on concepts. Likewise with programming, we're actually not going to do, we're going to be using R, but we're not going to be doing heavy programming, which would be required if we went into depth with things like deep learning. That being said, you should have some level of comfort with R. The more you bring to the table, as I think Dave Armstrong said earlier, the better off you're going to be. But you don't have to have you don't have to be a total pro at R. I use R instead of Python because, right, again, we're already limited in time and space as far as what we can accomplish. Getting into I like Python. Python's great. It's no knock on Python. But everything we need to do, we're going to be able to do with an R. And we're already going to have our hands full. Getting into Python would require, right, generally there's less familiarity with that in social science circles. So you'd have having to learn Python in addition to all the other stuff we're doing. So that's just an efficiency measure, not a statement on R versus Python. Yeah, and I don't think I have this on here, but we'll have 4 to 5 assignments. I think we actually usually are able to get out 5, but at a bare minimum, we'll have 4. And I think that's it. Yeah, thanks. Any questions?
I was wondering what kind of data are we using, and do we like create the training data and the test data, and we construct a model based on it?
Yeah, and I'm glad you mentioned that too. I think all these. Oh, I'm sorry. What kind of data do we use? Sorry. Yeah, what kind of data do we use, or are we constructing our own? All of these assignments, I think, except one, I encourage you to use your own data, so that those should all be amenable if you have your own data. I'm mostly going to be working with tabular data. I'm a voting behavior scholar. I think the ANES is a ongoing gift from God. It's one of the real just great accomplishments of humankind. And so we use a lot of NES data, National Election Studies, voting behavior data, as a way just to get a sense of some realistic data that isn't too specialized, hopefully. So we do that. We'll do some text. We won't go heavy text analysis, but we'll have that as well. But yeah, a lot of focus on, again, yeah, exactly this workflow of doing splits, creating training and testing sets, and optionally validation sets on top of that, and then tuning the model based on that. So mostly tabular, some text, and of course you're encouraged to use your own. Great. Thank you very much. Hope to see you tomorrow.
There we go.
All right.
Hey, y'all, my name is Mark Banning. I'm from Oakland University, not anywhere in California. It's the less exciting one that's about an hour away from here. So I live in Michigan. And I am teaching applied multilevel modeling with my TAs Valerie and Gina. So in the interest of time, we just dive right in. So my approach to this course is I want to introduce you all to all the different kinds of questions that you can answer with multilevel modeling. I realize I don't have a slide anywhere that tells anyone what a multilevel model is, so let me try and do that real quick. You might have had like a paper you're working on or something where someone says, oh, your data is clustered, you need a multilevel model. Yeah, it can handle clustered data where you have to worry about the dependencies of like outcomes being clustered within schools or what have you. But it's so much more than that. Let me try and build it up for you. Let's say we have 100 schools that we want to get data on the students from. We go into these schools, we sample a bunch of students, and we're looking at some relationship between X and Y. We're going to capture that with some kind of regression coefficient, right? All of those 100 schools can have a different regression coefficient. The mean of those regression coefficient, that's what we're modeling. That's going to be our fixed effect. What's fascinating, what's interesting about multilevel models is the variance in those effects that we're looking at. So it's not just about this clustered data. It's great to handle that, but it's like taking a sledgehammer to a wall when you want to hang a picture. These models can do like so much more when it comes to like understanding what's going on with those random effects. So that's what's really cool about them. What we assume in terms of these models, or in terms of what we'll need for the class, or what you need for the class in terms of prior knowledge, is just some familiarity with regression models. And it would be helpful if you have familiarity with interpreting interactions, because there are a bunch of them that are going to be popping up, and they're so fun to work with. These models are so cool. If you have no familiarity with regression, it's going to be a little bit difficult to keep up in this course. I've had that before, and then people end up dropping out. I don't want anyone to drop out because it's so much fun and I like seeing all your faces throughout the entire time. So if you have no familiarity with regression, maybe you want to backpack this course and get back to it. And in terms of organizing the course, it's going to be maybe half to 2/3 lecture, and then the rest of it is going to be hands-on, like diving into some data, fitting some models, like really just getting into the mess of fitting these models, messing them up, and then we all fix them together, because that's going to happen. Here's a basic outline of what we're going to be doing. For the first week, I introduce you to these models with organizational data. That's where we have individuals nested in some kind of organization, and we're modeling some relationship between X and Y. And then we'll spend some time in week 1 going relatively slowly so we can really start to understand these models. And then week 2, we kind of shift out of second gear into third, and they just start throwing a whole bunch of models at you. Because the way I love teaching this class is these models are mad cool, and they can answer a whole bunch of really neat questions with clustered data. And so I try to show you as many of the models that I think I can fit into 3 weeks to answer a bunch of different questions that you can have with clustered data. So we'll cover growth models, we'll cover different outcomes, dyadic data, cross-classified models, meta-analyses, and so on. If we have time, I try to throw in a couple of fun topics here and there. By the way, if there are any questions, please ask. I tend to get really excited and talk fast, which is what I will tell you in the first day of class also. So, okay. For software, we'll be using R for fitting the models, and then I just have all the data that we'll be using in SPSS. That's just for data management. The models themselves, we're going to be fitting and interpreting in R. And those are the packages that we'll be using. So when it comes to R, prior knowledge of R is going to be helpful. But if you think of R as like a really awesome, fancy Italian sports car, I drive it like a golf cart. So I'm just using it to fit, I'm just using these packages that I know how to use in R. I don't know R, like I can't pull back that hood and show you what's going on in that engine. But for these models, we'll be fine using the packages that I know how to use to fit these models. I like using R because it's free and the packages are free. And I want to make everything as accessible as possible. I do have a bunch of code from prior TAs who've used like M+, Stata, and SAS to fit most of these models. So if you use those software, we'll have those resources for you. For the grade, we'll have exercises as you go along so you can get your like feet wet with these data and with fitting these models. For the grade, it's just going to be a project. I like to be as efficient with this time as possible for all y'all. So if you've come in here and your advisor said, you need a multi-level model to do your dissertation, and you really want to graduate, well, bring your dissertation data and we'll use that for the project. Bring your paper that you're working on, and the viewer is like, why aren't you using a multi-level model? Let's fit these data, your data with a multi-level model, and we'll use that for the project. Let's be as efficient as we can with this time. If you don't have any data and you want to take this for grade, we're sitting in the house of data. We're sitting at the ICPSR. So we'll find you data that you're interested in along the lines of the topics you're interested in so you can do that project. Oh, my class is at 8:30 in the morning. I live up there in the upper left, and it's about an hour drive. Me and I have to get my kids to daycare at 7 in the morning. We are a well-oiled machine, so that always happens. So 7 in the morning, get them there, zip over here. Typically I can make it by 8:15 and I'll be at class in time. Fingers crossed. This morning, right about here, the highway shut down and we had to get off and come around. And then this morning also right about here, every entrance to M14 that I need to get here was blocked. I went through 5 different towns trying to get on, and it was always, I'm almost there. Oh no, that's blocked. So it took me 2 hours to get here this morning. That's not gonna be regular, but it has happened once in each year I've taught this class when I'm like, just traffic. It does its Michigan traffic thing. So 8:30 in the morning. If I'm there with a smile on my face, you can do it too. So come on in and take multi-level models. And okay, are there any questions? And I went through everything real fast.
And you should be all set.
Okay, and everybody can hear me in the room, on Zoom. Excellent. Why should you take Networks 1? Because it's all connected. Many of the things that we want to study are not independent, but in fact are interconnected and influence each other. So if you want to understand power and who wields power, if you want to understand how information flows or how conspiracy theories spread throughout a population, you need to understand networks and you need a network model. There are networks that you can find in really every field and every discipline, many social science fields, but even beyond social science. So if you're interested in understanding how various types of people or agents or countries or organizations might influence other types of agents, network models are for you. So if this describes you, can come to our networks class. The truth of interconnection is out there, specifically in Mason Hall on the afternoons during session 1. We'll cover many different things. We'll talk about network modeling, how to measure networks, how to think about networks, how to interpret network measures. We'll focus primarily in R. I do have some expertise in Python as well, so if folks are interested in Python, that can be an option. And we'll sort of get into an overview of various network inference techniques. In session 2, there's also a Networks 2 class, so if you're really excited about network inference, you can take Networks 1. This, in summer 1, get sort of the basic introduction, and then in Networks 2, it'll go into more depth on some of the inference approaches. There are 3 assignments over the course of the next 3 weeks, so 1 per week. The assignments will be in R, but they are designed to give primarily to give hands-on experience with using R. It's okay if you don't have much familiarity or comfort with R. We will walk through all the packages and steps of the R analysis that we'll be doing. You have the option for the assignments of either using your own data set if you have one that you're excited about and ready to go, or each assignment will also come with a recommended data set. So particularly if you're newer to R and you just want to learn how to load a graph or load a network into R and run some statistics, we'll provide data sets for you to use as well. I am Professor Sarah Sugars. I am at Rutgers University. I live in a communication department, although I'm also very political science adjacent. I have a very interdisciplinary background, and I love hearing all the different work that people are doing, particularly when it comes to things being interconnected. So I hope to see you tomorrow afternoon in Networks 1. Thank you. Any questions? Tried to get through some of the top hits of questions people have been asking folks. You don't need to know any linear regression. There are no prerequisites. Oh, sorry. There was somebody who asked a question on Zoom, which I was responding to, but. Okay, sorry. Yeah, so there was a question on Zoom about linear regression. You do not need to know linear regression. And in fact, we will also talk about why regression can be problematic when you're using interconnected data. Regression is great in other contexts, but can be challenging in network contexts. There are no prerequisites for the class. We'll walk through both the conceptualization of networks as well as different measures and things for how to think about and interpret and analyze networks. Okay, sorry before.
Like what type of models are they? Is it based on regression? Yeah, what is it?
Yeah, great question. So a network model is in many ways its own model. So you're modeling sort of things and how they are connected to other things. And so as you can imagine, a regression kind of framework is not helpful if you're trying to predict something that is interdependent and is not independent. So it will not use a regression framework, but is more sort of talking about the model itself of thinking about how things are connected to other things and how you can deal with that in a world where a lot of the methods that we might be familiar with, such as regression, don't really work, or it sort of breaks the assumptions of those models. Other questions? Please.
Just adding on to that, so are we going to talk about what works to deal with the network data set?
Yes, great question. No, nothing works, everything doesn't work, just give up. No, we will talk about what works as well. So we'll talk about sort of starting with really going into depth on some of these questions you're asking of like, okay, so we have things that are interconnected, like what do we do now? And just building those network models. And then we'll talk about, okay, now that we have a network of things that are interconnected, how do we actually analyze that and understand that? And like, what kinds of interesting questions can we ask? How can we answer those questions? That's what we will be covering over the next 3 weeks. Other questions? Yes, you can use network models for causal arguments. In Networks 1, we'll sort of touch on the landscape of making causal arguments and like the types of network methods that are out there. Networks 2 will then go into much more depth about those specific methods. But there are methods that can allow you to predict like what's the probability of observing a specific network, or what's the probability of observing a connection between this person and that person. And I think somebody asked about assignments. Yeah, so for assignments, there are 3 worksheets. They're all in R, although again, we'll sort of walk through the code that you need for those in class, and some of them will be more like free response conceptual questions, some of them will be more coding questions. And they're intended primarily to give you hands-on experience with network models. So like the first assignment, for example, is load a data set into R and just sort of going through the basics of being like, yes, you can open R, you can get the data into R, you can sort of get a basic measure about this network, and we'll sort of then build up from there. But the focus is really on understanding or sort of getting hands-on practice with these methods and with these kinds of models. Please.
Example of like the analytical leverage of like for instance, someone were to consider like a potential project, how would they go about getting the kind of data that would be like network specific, and what can they do with it beyond saying this is how we can quantify how connected people are, but to say here's how that relates to X variable, and the thing is X variable can tell us that has an impact on how connected people are. You know, like how can you give us an example of how we can use these?
Sure, yeah. So the question was sort of how can we use networks, and also how can we collect network data, which are both things that we'll talk about in this class. In terms of collecting network data, there's a lot of different strategies. There's a lot of work that uses survey methods. So you literally ask people like, who are your friends, or variations of that question. There's also work that will use more of like sensor technology. So if people have like, you know, even just like a cell phone, and you can see, oh, people's cell phones are near each other. You can use that to say they're physically proximate to each other. I do a lot of work on social media. So looking at things like who reposts whose content can sort of define what the network is. In terms of the kinds of questions that you can ask, there are many of them, but oftentimes, like because things are interconnected, it's often questions about who has influence, how things are spreading, thinking about what interconnections there are between things. So a lot of work also will look at like what's the probability of people being connected based off either demographic characteristics or political ideology or something like that. They're all fantastic questions. I'll also be around, you know, for the dinner, whatever's happening after this. So if people have other questions, I'm happy to chat.
So the last presentation, we all made it. I'm glad to be here. My name is Naomi Newbin-Sellers. I co-teach the Race, Ethnicity, and Quantitative Methods course with Ozan Kalkan, who is my co-instructor. For the course, I had a whole bit. I'm just gonna go ahead and jump right in after this long, you know, what time is it? Few hours, and just talk a little bit about the class. So as I mentioned, I co-teach the course with Ozan, along with our two amazing TAs, Amanda and Michaela, who are out there in the back. The course is it's a lot of things, right? The course is.
Clicker if you want.
Oh yeah, that would be super helpful. Okay. So the course is a lot of things, right? In the first few days, we really delve into not how you define yourself. That was a question that I was going to pose to the audience, to just think about the complexities of how we conceptualize identity. We're both political scientists by trade, so you see emerging work that thinks carefully, well, tries to think carefully about how we think about racial and ethnic politics within a broader society, but also the impact of racial attitudes on political behavior in a myriad of ways. But what makes this course unique is it's interdisciplinary by nature. So we'll have one exercise where we asked students to bring an example of how race ethnicity is studied from their own discipline, to just talk about the myriad of ways that race ethnicity has been quantified and how that's impact the way that we think about socialization processes more generally, which I think is just a helpful exercise. So we'll think some about how definitions matter for measurement practices, which I think underlay many of the courses that you've heard some of my colleagues talk about previously, but also to think carefully about race ethnicity and its implications when making inferences in our own work, regardless of disciplines. We talk about the universe of definitions. These were just a few examples. I took a bunch of things off because there are definitions for ethnicity, but also definitions for race that allow you to think about race and to use an analogy from one of the pieces we'll read in the class as a bundle of sticks. So thinking about the elements for how we conceptualize race, not just thinking about how you might identify me or how I might identify myself, but also the things, those kind of targeted ideals or the concepts that underlie what we mean when we say race or ethnicity. Definitions and distinctions matter. They matter for many ways, but in the context of this course, they matter for, they tell us how to build and evaluate theories related to race, but also think about kind of what I mentioned earlier. What are we trying to explain by evaluating race, which I know is also discipline specific. And allows us to link theory to measurement in a really meaningful way. So we need to conceptualize, we need to have valid definitions for how we think about race and ethnicity, and it allows us to do all of these kind of helpful processes when we are attempting to explain some phenomena, but also how race ethnicity relates to that phenomena. There's another part of this that also talks about, I think I'll just point out, thinking carefully about how we're identifying and operationalizing concepts, which I think is race ethnicity is not new, especially if you come from sociology or one of the fields who have thought critically about race for a very long time. But I think what we tend to do is to think less carefully, especially in the political science discipline, about what we're saying in the relationship between X and Y. What are we saying by race is driving something? So we try to think carefully about the concepts that underlie how we think about race ethnicity and what that means for how we are studying racial attitudes and behavior. So there's so many challenges. Why do we do this? I mean, we do it for all the reasons, right? We want to know. We have endless questions, and this doesn't, I'm not saying this to say that you'll come to the race class and I'll answer the questions. That is not what I'm saying. What I am saying is you may leave with more questions than answers, which I think is also helpful for the way that we do science. So many challenges, but so many unique opportunities to think about the relationship between race ethnicity, but also how we quantify that in our own disciplines. Specifically, prerequisites, we don't assume any prerequisites. I think we say that to say that regardless of what background you come from, all perspectives are welcome, whether you've primarily done qualitative research or whether you come from a background that doesn't really have meaningful discussions about race, ethnicity as they relate to some phenomena you observe through your own research. Come and let's talk about it, and we can have a meaningful conversation of what that means as you move forward to your next steps. So regardless if your goals are, academic scholarship or whatever, we can come and have a meaningful conversation about quantitative social science in the specific and unique context of race. We'll focus on dimensional analysis, some measurement and variance. That should say experimental methods broadly, and then some survey design. Oh yeah, that's all I got.